Nah, perhaps. Okay. Yeah, we live.
Sounds good. You want me
Yeah.
to start?
Now let's just wait a little more for people to arrive. We have already 10 people. Just wait a little more and then we can go.
Sounds good. People can stare at my dog for a while. At least one of them.
Remember my dogs? Have been 6 years I don't see my dog.
No.
Yeah.
Oh, I'm sorry to hear that. I'm happy. Because I work from home, I'm able to see my dogs every day.
Oh.
And I have a cat that basically lives in my office. So
Oh. That's really cool. Now let me invite more people. Let me just go here and share alive. Okay. Yeah, Adam, I think we can start.
okay, sounds good. Well, welcome everybody. Thank you for coming. My name is Aaron Ballman, and I want to talk to you a little bit about compilers and programming languages at a super high level to try and convince you that these things are attainable. They're things that you can write, I can write, anybody can write, and again, work on. So they are not created by unicorns, rock stars, or ninjas. It's real people, and sometimes with the help of our pets, but not always. It's not going to be a talk necessarily about how to write a compiler, and it's not going to be a talk necessarily about how to write a programming language. It's going to be a little bit higher level than that. So kind of one of the first questions is how would I know anything about this stuff? I actually went to school for game programming for video games, and it was complete accidental luck that got me into compilers and programming languages. I worked for a company that built a compiler as my first job out of school. And one day they just told me, hey, we'd like you to work on the compiler. There were only 4 engineers in the company, so things kind of got split amongst all of us. And that's how I ended up getting into compilers. And it turns out that it's actually a lot of fun. I really enjoyed that work. And so I ended up building a career out of it. And I'm currently a maintainer for Clang, an open source C and C++ Objective-C and Objective-C++ compiler. And I'm also a member of both the C and the C++ standards committees, and I can confirm that I am a real person and not a mythical being. So compilers, they're not magic. It turns out that compilers are actually a relatively simple concept that gets applied over and over and over again. The idea is take a piece of information that's too difficult for you to reason about, find a way to simplify it just a little bit, and then do more processing on it. And you repeatedly go to easier and smaller and more easy to reason about forms of that of the source code until eventually what you wind up with is a machine executable code. So as a good for example, you could take C++ code and then decide to turn it into an intermediate representation that then goes into an assembly code that then goes into an assembler to turn it into machine code. And then you'll finally end up with your executable code on the other side of things. But this is a pretty common pipeline for all languages. So kind of all compilers do this dumb repeated transformation dance. But I'm going to be focusing primarily on C and C++ compilers in this particular talk. And I'll try and call out places where things might be a little bit different. So there are 2 halves to a compiler. You've got a front end and a back end. And every once in a while, you have people that will claim that there's a thing called a middle end that sits between the 2 of them. But really, you could kind of think of these as being two different halves of the same functionality. So the front end is doing what most people think of as compiling. So it's taking the user's source code and it's checking it to see, does it meet all the syntactic requirements of the programming language? Like, can I find the syntax somewhere and match it to a grammar to determine what the user actually meant? And it also takes care of like the semantic analysis side of things, which are things along the lines of, does the operation make any sense? You know, can you add a pointer and a float? And so the front end is doing a lot of the work that users typically think of as compiling. And the back end is the part that where all the magic happens, which is it takes all of the simple high level stuff about here's the language, and then it tries to optimize it. And so by the time things get into the back end, it's usually at a very, very low level format, kind of like an assembly, or perhaps one step above, a little bit higher level than an assembly. But it's usually repeated instructions: add this, subtract that, store it into this. And so it's kind of lost a lot of its connection to the original source code. But it will be what's responsible for taking care of your source code and turning it into something that works fast. So going into the front end a little bit more, at least in terms of C and C++, the way that this typically works is you have the front end will take the user's source code, which is just text. And computers don't understand just text. They understand ones and zeros. So the very first task that the front end will do is it takes the text of the source code and it tries to turn it into tokens. And a token is just an abstraction of what the user wrote. So the user could write an identifier, foo and bar and baz and quux and so on and so forth. But from the compiler's perspective, those names are kind of, they're useful and they're helpful and they're necessary, but they're not easy to reason about. And so it says, no, these are an identifier, and you can ask for more information, like what is the identifier? What's the name of the identifier? Or as another example, you might have numeric constants. You have 0, 1, 2, 3, all the way up to 9. The compiler doesn't try to reason about those as individual things. It goes, oh, well, you know, everything here is an integer number. It's an integer constant. So we're just going to treat all integer constants the same. And when you need to care about the value, you can ask for the value. And so that's what I mean by it's kind of simplifying the source code, is it's taking those source constructs and turning them into tokens. And in the context of C and C++, this is typically also when preprocessing happens. So people think of the preprocessor, historically, the preprocessor has always been a separate thing. So you give your code to the preprocessor and it preprocesses it. And then you take that output and you give it to the compiler, and then the compiler compiles it. But that's really slow in practice, and people like having fast build times. And so we kind of smush those things together in practice and decide whenever the compiler says, hey, I need a token, then if it turns out that that token would be a macro, it just goes and expands it. Or if it goes, oh, this was in pound include, instead of making the compiler figure out how to deal with pound include, the lexer will actually go find the file, open it up, and say, oh, here's the first token from that file, instead of making the compiler try and do it. And the thing that's driving this lexing is the parser. The parser's job is to consume these tokens according to the language of the grammar. So it's the part that's doing the syntax checking. So if you enter in punctuation that doesn't exist anywhere in the language, it's the parser that starts complaining about it, because as it's walking through the tokens, trying to match them to a grammar, it goes, I don't know what you're trying to do here. And so it will give you your syntax error. The semantic side of things is what's consuming all of that parsed information. And so it's doing all that semantic checking. The parser and Sema work really, really close hand in hand together. And so what will happen is as the parser finds things, it will go, hey, I found an identifier. Does this match what you expect it to match? Or I found a parentheses that makes this look like function call. Is this actually calling a function, or are we trying to put parentheses after a variable declaration? Type int. And so the Sema stuff is really what's doing most of the heavy lifting in terms of giving you warnings. It will still give you errors, and the parser can certainly give you warnings instead of errors. But Sema is where I would proclaim, more than half of the parsing, or more than half of the logic goes in terms of telling you when you've messed up and your code does not make sense. But the output of SEMA is generally an abstract syntax tree. And so the idea here is it's taken those tokens from the source code, and the parser has parsed them down and figured out, oh, I have an addition operation. It's a binary operator that's a plus, and it's got a left-hand side over here, and this is the expression for the left-hand side, and it has a right-hand side, and this is the expression for the right-hand side. So it forms this tree of semantic constructs from the language, and this is super powerful because then other things can consume that AST for whatever needs they have. So for instance, CodeGen will consume this AST and it will go and produce, say, an intermediate representation to give to a backend. But you could have a static analyzer that consumes that AST and says, oh, well, from this information, let's make a control flow graph to see how data flows through the program symbolically, and maybe we can come up with different diagnostics from that. Or as another example, you could have the AST and you decide, what, I want to pretty print my source code so that it comes back out in whatever formatting the compiler thinks is the most aesthetically pleasing. And so it can walk over the AST and print out each one of those nodes as it traverses it. And you'll wind up with better formatted code. So there's all sorts of things that you can get from these abstract syntax trees, and that's why modern compilers typically wind up using them. Now, I should pause a moment and just mention, not every compiler is built the exact same way. So there are C and C++ compilers that don't use ASTs. It turns out that that's a little easier for C than it is for modern C++. Trying to deal with modern C++ and things like lambdas and range-based for loops and that sort of thing gets really, really tricky when you don't have an AST. But it is possible because Microsoft did it for years. So in terms of the backend side of things, this is the part where optimizations are translated from one form into a better form. And better is really wishy-washy. Better might be faster based off of what instruction set you're going to be targeting. It might be smaller code. There's different forms of what people want to optimize for. But each one of these optimizations basically is set up as a pipeline of passes. So the idea is you take intermediate representation from the front end and you give it to the very first part of the back end and say, here, start optimizing this. And it's going to do something. Maybe it's going to dead code strip. So it's going to find all the places where it goes, oh, this is unreachable code. Let's just remove it entirely. Once it's done with that, you have a better form of what you originally had, and it will pass it on to another pipeline. And that other pipeline, the other pass, might do something like go, oh, we can replace all of these arrays of structs with an array of individual elements of the structs, or whatever it might decide to do. And the output from that will be better, gets passed on. And sometimes these passes even wind up getting repeated multiple times. So you go and you simplify the code by removing all of the dead code from it, pass it on to a couple more optimization passes. Those do other things like decide that they're checking for null pointer dereferences and goes, oh, well, you could not possibly have a null pointer here. Then it might go back to the dead code stripper and say, here, see if you can strip out even more code now that we've got more information and we've simplified it a little bit more. And the dead code stripper might be able to go, oh, well, these if statements can now get pulled out because this other pass has given me more information. And so this thing kind of works in a little cycle where it goes and pass after pass after pass after pass. And eventually the optimizer says, I'm done, I give up. No more passes are really going to get a win here. And so it's that point in time when you start getting the output from the back end. And that output could be assembly code, it could be machine code, it could be anything that the back end decides it wants to output. Information about what optimization passes ran and how successful they were, that sort of thing. But the back end winds up pretty much just looping over these optimization passes over and over and over again until you wind up with a better form of your code. Which brings us to the fact that there are other parts of the tool chain. So the compiler, the front end and the back end stuff is really just one part of what you need in order to get a decent programming experience and an executable output even from your program. So for instance, linkers are another tool that you'll run into often. And this is because the compiler, the front and the back end, will compile one source file at a time. And it will give you a bunch of object files, and those object files correspond to the original source code. But something needs to take those object files and push them all together and produce your actual running program. And that's the job of a linker. So the linker will do that by basically trying to merge all of this executable code together. And we'll also verify things like, oh, do you have a function named Maine somewhere so that we know where we're entering into the executable and that sort of thing. Other tools would be things like resource compilers, which are used on Windows and Mac Classic, and debuggers, profilers, code coverage tools, unit testing tools. There's a whole host of things that can come along with your compiler tool chain that are kind of outside of the view of the compiler. And so this has kind of a natural tendency of the C and C++ language is written with the assumption that the compiler only ever sees one translation unit at a time. And so compilers are set up to only ever really care about one translation unit at a time. So there's a connection there between what the programming language model is and what the compilation model is, which is pretty unsurprising, I would hope. But all of these parts of tools are written by everyday people. So Clang went and checked, they've got over 2,100 contributors. And when I was looking, very many of them are just individuals who contribute a few things. It's stuff like, I got an error message on my code and this error message is terrible, so I decided to go and change the compiler to make the error message better. Or sometimes people have a particular feature that they're like, I really love if const eval, and I want to make sure that the compiler has it. So they might go out and implement if const eval. And so there's people who will do these sort of individual contributions to Clang quite frequently. There are corporate backers as well. There's people like Intel and Google and Apple and plenty of others. But it's a surprisingly diverse pool of people. And speaking for Clang specifically, it's a pretty welcoming community of people and a relatively approachable source base for a compiler, for a C and C++ compiler. Mind you, it's still complicated because these are still large pieces of software. But in terms of just the code layout, it is something that's a bit more approachable for people who are interested in seeing about compilers. And that's actually how I got into this in the first place, was I had gotten into compilers at a compiler company, and they were doing things that were not C and C++ based. I eventually moved on to a different company, trying my hand doing color science of all things. And I got sad that I wasn't doing compiler work. And so I started hacking on Clang, having never worked on a C or C++ compiler before. And that was really just how I got introduced into the community. And so one thing is if you are ever interested in doing any sort of compiler work, I'd highly recommend giving it a shot. Don't be afraid. And don't feel like you have to be perfect, because like all software, compilers too come with bugs. I just noticed that this Clang bug database has over 52,000 bug reports. No, some of these are going to be feature requests and some of these are going to be invalid, but this definitely shows that like compilers are not infallible and the people who write them are also not infallible. So if you're interested in getting introduced to these sort of things, I would highly recommend giving it a shot and just trying it to see. So before we move on to the next topic, I'd like to just pause a moment and see if anybody has questions about compilers in general or anything that I've covered so far. I have no idea if people actually have the ability to ask questions. So,
yeah, I think I have my personal question. For example, one of the things that make parallel programming a little bit harder is the fact that compiler and microarchitecture can perform optimizations that are unaware of multi-threading, and they only preserve the semantic of a single thread programming. The question is, what it takes to enable the compiler to still perform optimization when taking in account, I don't even know if it's really possible, but just asking if you have, for example, you have two threads that are sharing, two threads that are sharing a global variable, and you want to perform optimization taking in account two threads at the same time. What it takes to perform such kind of optimization, for example? Because I think that's the things that make that's make parallel programming harder, right? Because if we don't actually, if we I think if we reduce actually not totally prohibit optimization, but just find a way to optimize by taking into account this multiple context of a program being different threads, I think it still can provide some performance.
Yeah, good question. So you actually hit on a really interesting topic, which is a lot of times the problem with optimizations is that the compiler just doesn't have enough information from the source code. So the user wrote source code that's perfectly clear, and the compiler is just simply too dumb to figure it out. And so a lot of times what people do in compiler writers is we add attributes, and we give attributes, we allow users to write attributes to basically give those hints to the compiler and say, hey, please unroll this loop, like, hey, please unroll this loop 8 times specifically, because I know that's going to be fast, and the compiler might not be able to figure that out on its own. And so for a lot of these sharing things, part of the problem is in C and C++, you have a global variable, and we have to assume it's shared because it's global. And there's no other syntax, there's no other marker anywhere that says, I didn't share this. And the compiler can't necessarily figure that out without looking at every one of the translation units. And that means the backend doesn't know. So the backend has to assume, oh, it's global. Somebody could be sharing it somewhere. And so a lot of times, if you can give information to the compiler by basically saying, I promise this is not shared, and if it is, that's my fault, I'll take the blame, then you can start getting better optimizations from that sort of thing. One of the alternatives to that is you can do link time code generation, which is basically the only point in time when you will see all of the translation units at once and go, oh, I can reason about the whole program now. And so link time code generation has a whole lot of benefits for these sort of things, but it's also a challenging time because it's gone through so many different processing steps before it gets to the linker. And each one of those steps simplifies things a little bit. So by necessity, you lose a little bit of information. And so it may or may not be possible to do at link time, but that would be about the only other time that would be plausible to do without making the user actually change their source code. Does that answer your question?
Yeah, I think yes. Another point that you mentioned about saying that the compiler is down because it cannot figure out a lot of information. Yeah, I think there is a trade-off between compiler and hardware on optimization, because there's the question that when I was start studying, I said like, oh, if the compiler performs optimization, why the hardware also perform optimization? So when I come up with a solution that there is the difference between hardware and compiler, because the compiler is statically, you perform static scheduling, while the hardware performs dynamic scheduling. But what actually happens is that sometimes the compiler and the hardware are doing the same job, right? So there is an overhead because they may be trying to optimize the same thing. So the compiler performs a nice optimization, but the hardware will also try to optimize what the compiler already did. But the hardware does it because the hardware doesn't trust the compiler. You'll say, oh, the compiler may fail. I cannot trust the compiler that he actually did it. So I will anyway be able to perform optimization. And I found out that hardware optimizations are very, how can I say, it's just really a machine, right? There is parts of the hardware, of course, where we actually have intelligence, because the compiler will start to have a special hardware inside of pipeline that can perform prediction, and the data that the hardware uses to predict or to optimize is at runtime, and it can change according to the behavior of the program. And hardware is going a lot in this direction, almost practically everywhere. Start from memory, for example, inside of memory controllers. We try now to look at pattern of access and so on. And I think it's really important to understand what the compiler can do, what the hardware can do, but also talking about sequential consistency, for example, where people it's also really linked to parallel program that we are saying. For example, we're trying to say to the compiler and the hardware, oh, no optimization at all, because you violate everything, and I care about the semantic of my programming, the semantic of my program, so no optimization, because you may perform optimization that will affect the semantic of my program. But there are actually people at hardware level, for example, that they propose to speed up sequential consistency by using prefetching and speculation. But actually, most of the hardware manufacturers today, they give up mostly in this idea, because the hardware that needs to perform this speculation can waste a lot of power to detect when the hardware violates sequential consistency, and also the hardware that is needed to perform state recovery. There is also people that do it at compile level. At LLVM, for example, they try first to remove the out optimization, and there was like 30% of the performance downside. But then what they did, they changed the optimization, that instead of violating sequential consistency, now we embrace it. We just change the optimization, and then the performance was the performance loss was about 5%. Yeah, but it's just at compiler level, because even if you perform, if your compiler cannot introduce data races, you still have affect the semantics of sequential consistency. You still have the hardware that you need to be aware of that. So, and I think it's another problem, and many computer architects today are trying to work in the whole stack. You have the compiler, and you have the hardware. And the example that you did, for example, attributes, it's really important, because even hardware today, computer architects are also proposing using things like attribute to solve some problems, for example. And we have the C++20 likely and unlikely, for example, attributes. That is really, I think, is a proposal that we have it because hardware today, they provide it, for example. Well, we can figure out if the break is taken or not, because your software may be too complex. Okay, you tell us, and we will trust you.
Yeah. No, and that's exactly correct. I mean, we at the end of the day, we have to trust that the programmer writes the things that they intend. But in terms of, you bring up a good point that, the compiler, the back end of the compiler will do optimizations that sometimes the hardware already does for you. And so it seems kind of silly, like you're doing the same work twice. But one of the reasons for that is there's so much variance in hardware that it's actually easier just to assume that the hardware can't do this and write it once so that the back end will do that optimization. And it turns out that we wasted a few cycles on the compilation side of things that we didn't have to, because the hardware would have done it for you. But that's better than the alternative, which would be things like trying to determine how each and every individual chipset works for a CPU and decide which code path you want to take for the optimizations to save a few extra cycles. Means your code becomes much more difficult to maintain in the back end, because you get more code by necessity. So it's a hard trade-off, because you don't want to do the work if somebody else is going to do it for you already. But at the same time, if you can't trust that it's going to be done on the back, if you can't trust it's going to be done on the hardware.
Yeah, you still need to perform. And the another important things that we actually need to understand, there is things that compilers can actually not do. For example, how the compiler can tolerate true dependencies, right? That is right after a read. For example, you have an instruction that is writing to a register, and the subsequent instruction is a read, right? The compiler can do nothing there, because the compiler knows, this second instruction here depends on that one. Well, okay, the compiler can do something. For example, if the compiler knows how much time we take the first instruction to complete, because the compiler can place another instruction that is independent if the compiler is aware of the microarchitecture, for example. But I find out it's too hard, because, for example, the first instruction can be a load instruction, and a load is a variable latency instruction, because if it hits at level 1 cache, it can take 2 or 3 cycles. At 32 caches, it can take 4 or 7 cycles. At 33, and to my memory, it can have a page fault, and the page is not actually in memory. And how the compiler can know that if it's a load, how long this load will take, because if the compiler can reorder instructions so that they can use the hardware that is free instead of instructions. So I think this is one example where compiler cannot do too much, because the hardware today is too dynamic, it's full of dynamic events, for example, things that change dynamically too much. And I think even if compiler try to do profiling at runtime, it may affect another problems, like, today people are already complaining the time that take to compile a program, for example. And if you do a lot of runtime, compiler time checking to figure out things that maybe even the compiler, we need to think, okay, this thing can be true here. What about in another architecture or in the same program? May have something that can change it dynamically, so it can be wrong. So it can be kind of probability, and the compiler will still need to inject code if that thing really doesn't have. So I have the safe code, the safe path that your software can take, and it's also increase your size. For example, trace scheduling, and I think it's known to know that there's things that compiler cannot do. It's just simple for the hardware to do, and there's things that the compiler can do. And I kind of think that compilers tend to be, a little bit more formal in terms of it tend to flow analysis, for example, in terms of compilers, even though hardware also doing tracing of instructions also kind of look like a flow analysis. But I think it is really exciting topics, this compiler optimization. And I think that in the times of very long instruction word machines is really when compiler people was actually trying to do a lot of stuff, because hardware need to be so simple and everything was in the burden of the compiler engineer, for example. And I would like to comment your point of view on very long instruction word machines and very long instruction compilers, for example.
I actually haven't had much experience with them, because most of my focus has always been on the front end side of things. And so by the time it goes to the back end, that's somebody else that's making those determinations. So I don't necessarily know a good answer there. But you do bring up a really good point with regards to, you are right, the optimizer or the back end doesn't necessarily know how long a load is going to take or those sort of things. And one of the situations that can help with that is profile guided optimization. So if it's, I have a data set and I want that data set to be the optimized path, then sometimes even if the compiler can't figure it out and you don't have any annotations to tell the optimizer what to do, doing profile guided optimization helps, because you're basically just telling the optimizer, these code paths, the hot paths, are the ones that are the most important to me. And so it can't still answer the question of how long will a load take, but it can still eke out extra performance that you wouldn't be able to otherwise get. So we come up with all sorts of tricks to try and make it so that you don't have to write extra code but still get performance.
So we have a question here from Daniel. Is that does Inter contribute to C lang as a front end?
Yes, there's actually a few of us who, the front end team is probably like 15 people, give or take. And what winds up happening is there's a few of us who will take some stuff and upstream it, but there'll be other people who may have done that work for us beforehand. So that'll be fixed in our downstream in ICX. And then we'll go, let's bring this up to the Clang community. But there's a couple of us, myself, Eric Keene is another one, who we predominantly work on Clang as a front end. And ICX still gets all those benefits because it comes down to ICX eventually, but we try to do as much as we can inside of the Clang front end, just because that's really the best for everybody. So great question.
The another question is, Orlando says that he's always afraid by the complexity of making a compiler.
Yeah, they seem overwhelming at first, for sure. And when you start working on something like a language like C++, it is overwhelming. That's a huge language. Like, I would not try to write C++ as my very first compiler. If you're worried about the complexity, sometimes picking a simpler language and going, okay, I'm going to try implementing this simple language first, makes things a lot easier, because you start learning all the concepts of things like, how do I lex, how do I parse, errors are a problem, those sort of things you get to cut your teeth on with a much simpler language. So you could pick something like C89 as a good example. That's a pretty simple language to implement a compiler for. There are some members of the C committee who claim it can be done in a weekend. I don't necessarily believe them, but but yeah, the best way to kind of remove some of that fear is to just a lot of times just dive in and give it a shot, and find other people who can help you too. So if you have questions, asking others is always a great help.
Someone asked, Eliandro again, how does the debug breakpoints work? Are they added at compile time? How are they intercepted?
So I think it depends on the compiler. I know that there are, sorry, let me rephrase. I think in terms of, there's two ways you could do debug breakpoints. The programmer can manually insert code into their code that says, please break at this place. Those breakpoints are not added. Those are the ones that are added at compile time because the user wrote explicit code to do it. I think on Windows, there's a debug break function that you could call that does it. And I'm pretty sure it's like int3 was the old DOS code for it sort of thing. But there were ways that you could basically say, please break into a debugger at this point. But when you're running from within a debugger, that's a totally different beast. The debugger itself isn't going to do anything at compile time because the debugger is not known at compile time. It's just not a process that's running when the user's compiling. And so a lot of times the way those tend to work is you can insert instructions directly into basically edit memory and insert the debug break instruction in there. You can do things with page protection and that sort of stuff. That's usually how like data watch points tend to work, where you're saying, please show me when this variable changes its value. A lot of times that's just protect the page of memory so that if the user tries to write into it, it makes an exception and the debugger catches it and says, oh, cool, I'll tell the user this is changing now. Debuggers are a fascinating thing. I don't know necessarily how they work.
Yeah, for debugging, the architecture provides some special registers that I think that are used to provide debugging in the system. So it's not only rely on software. For example, in x86, for example, there are special registers and special interface that the architecture provide to perform debugging. And the one question here is, how many years do you took to master compilers?
I'll let you know whenever that happens. I've been working on Clang since 2011, I think was when I first started in. So 10 years now is working on Clang. And I don't feel like I've mastered it despite being a maintainer and a code owner. That's largely due to the fact that Clang compiles C++, and C++ has a lot of it's got a lot of just interesting stuff to it. So like template instantiation is a good example. There's a whole ton of machinery around how do you instantiate a template, and you can work on the compiler and ignore that very easily because it's like, if I'm not working on template things, then the template stuff just does whatever it does. And so you can kind of start to build up your expertise in like little niches within the compiler. But I don't know that I would ever claim that I have mastered, say, a C++ compiler front end as an entire whole. I think there's only maybe one or two people in the world who could make that claim legitimately.
Yeah, and I personally would like to know how, for example, what is today people of course it's better for some people actually, if maybe for most of people, if most of our program could be executed at compile time, so that we can, of course there is overhead, but maybe the overhead is the downside of it is time at compiling. But maybe it's good because now we execute less. For example, when you deploy your application, I think it will be important for people to know, how does the compiler perform? What's happened at compile time when the compiler is actually executing compile time instructions? Well, let's say, if we can say that way.
Sure. So C++ has actually done this in that we have the const_expr keyword. And so in const_eval and const_init and all sorts of other keywords around this to basically say, do everything at compile time. And in true C++ fashion, we got the defaults wrong. What we really would have liked is we would like everything to have been executable at compile time, except for the things that you say, no, please do this at runtime. So we would, kind of wish we could do it opposite to how we did it, but we had to slow roll and introduce this slowly, and that's why we are in the situation that we're in. But this has turned C++ largely into an interpreter. So the compiler has its own engine to try and do symbolic execution of constant expressions. And it is really a compile time performance hit in terms of the more stuff you do const expr, the slower your builds are. But it's a really big win in two ways. One is, if you're doing this work at compile time, then the developer compiling stuff is the one paying all of that cost, that runtime cost. But it means that the people who are getting that executable, they don't have to spend the cycles doing those calculations themselves. So you do get the optimization benefits. But one of the bigger benefits that I personally think is there is you can't have undefined behavior in a constant expression. And you can at runtime. And when you have undefined behavior at runtime, who knows what's going to happen? It's probably not going to be good, though. And the fact that the compiler is required and obligated to tell you, I can't do this, you're asking me to divide by 0, and that's nonsense. That is actually a super powerful property for just checking correctness of your program. I mean, literally, you can write your unit tests with static assert at that point. And if it compiles, it's correct, which is, kind of a holy grail of C and C++. So does that answer your question?
Yeah. Yes. And the other question that I have is, for example, there is, of course, Clang, for example, we saw that there's I don't know how many years people have been, how can I say, developing Clang, for example. Clang, I think the name is Clang. It's just sometimes English and Portuguese I overlap.
No worries. I've heard it both ways.
Okay. Clang, for example, people have been building Clang for a long time now. And the question is these techniques of developing Clang for generating code. For example, how is it updated to target, for example, new architectures, for example? I don't know if it...
So the backend side of things is set up very modularized. And so adding a new target to a backend it's a lot of work because it's a new target, but at the same time, it's pretty reasonable from what I understand. So I know people have been bringing on new architectures like RISC-V and that sort of stuff. And over the years, we've certainly added tons, like all the different ARM architectures and that sort of stuff. And so it is fairly insular, but there are surprising challenges that when you start getting into the details of stuff, it gets a little more difficult. So for example, calling conventions is one of those things that's kind of split between the back end and the target architecture and somewhat in the front end side of things, because it affects how you pass parameters and how you get returned values. And do you pass, is there a stack or is there not a stack? Like those sort of questions. So it can be involved, but it's not nearly as bad as you might expect. So if you had, your own particular hardware that LLVM doesn't currently support, it's certainly possible to add new backends to it. And the community is happy to take those so long as someone's interested in doing the maintenance work. It's really what it boils down to is long-term, who's going to be responsible for giving this love when there's problems with it.
Yeah. Yeah, because you have now multiple people dealing with different targets, and also these people need to currently be aware of the updates that come out for a particular architecture, because now what happened is the compiler will start generating, need to generate new code, because you need to use the resources that are now available in the architecture. For example, if let's see, we have a compiler in the architecture, let's say, for example, x86, where right now, for example, you don't need fences, for example, to implement some C++ memory models. But after maybe 10 years, the x86 break that rule, and now the people maintaining the task need to update that now we need fences, right? Because thing is over. And so maybe for this instructions or update in hardware that are made that can really affect the software, that the developer can notice, the people can really work hard so these things doesn't happen. But let's about these instructions and updates that can provide performance, but the user, right, using the compiler cannot feel. How the people work on compiler to target really maintain update in order to keep providing state of the art translation.
I see. So a lot of times, different companies that produce hardware just have back-end people that are working on it. And so like Intel has a bunch of people that work on the back end for the Intel architecture stuff, and AMD's got a bunch of people who work on the AMD back-end architectures and so on. And so a lot of times for the major architectures, the assumption is the hardware manufacturer is maintaining that. By and large, though, hardware manufacturers try not to change the instruction set such that it's going to break anyone's code, because that code might have been compiled 30 years ago and is now running on this new processor. And so there's really no chance to recompile it to get that different behavior. So they try really hard not to break backwards compatibility. Still happens sometimes, but more often it's we've given you new instructions or a new model or something along those lines. And the risk there is usually a little less, because if you don't implement it right away, no one's code's broken. It's just a little bit slower. And believe me, users will tell you, hey, my code could go faster if you just changed this a little bit. And so like there's usually a feedback loop with users that we go, oh, we forgot to go and update this for this new thing.
That's what I was saying. Like, not necessary to break. It just gives you a different version of it. It's what actually x86 does, and most architecture does. They will not break. They will just go. There is the old thing. It's not optimal anymore. We have the new thing. For old software, you can for the code you already compiled, it's okay to work. But for new codes that you will translate, for now, since now you need to use this instruction, because now we have support for that, and this is what we give performance. And also, I think the compilers actually plays a really big role in this in the business and industry around, especially for the hardware manufacturer when they try to build new architecture, because they know will the compiler will the codes that was already translated, right, using in the past, can run on a new architecture, for example. And I think it's a big question. But the question that I really have is, maybe I know there is business part, there is all of these things that is important, but sometimes I may be wrong, but sometimes I think that the industry need to change, and industry and companies and people need to understand that software need to change, right? And I think that backward compatibility, right, to guarantee backward compatibility is I think it's stopping us from evolution sometimes. For example, we want to go forward, but we cannot, because we need to keep dependencies and backward. And there is people actually working hard, bringing new ideas for implementation, but we can't use them because we need to keep supporting old software. I understand the business part. I understand that there is money, there is all of that. But I think maybe we should, maybe it's time to start really thinking that software from today is okay. Don't trust this to be forever, right? From time to time, we need to break and we need to update. For example, because I think it's important.
It's kind of fun because you're touching on one of what is probably the most hot button topic in the C++ standards committee. And it's been a hot button topic for ever since I joined the committee, which is ABI, not API, but application binary interfaces. And ABI is basically the way in which it's a code word for saying, this is stable. You've made a binary, and the calling conventions and all of the ways in which you interact with this binary need to stay exactly the same. Otherwise, things on the other side of it will behave poorly. And you're absolutely right. This completely stymies progress sometimes, because we'll go, well, we'd like to fix this problem, but it's an ABI break. And so as soon as we do it, everybody has to recompile everything. There's a couple of practical problems with this, though. And this is why we keep running around in circles around the topic. It turns out, not everybody can recompile their code. there's a whole shocking amount of professional software that they just don't have the source code to anymore. And so I have, you have a DLL somewhere that you got from a third party that went out of business 20 years ago, and the DLL does what you need it to do. But if you can't recompile it, you have kind of a problem. It's a chicken and the egg issue. It's tough to recompile the things for which you don't have the source code for. And so we haven't come up with a satisfactory solution, but there's a whole lot of people who are very driven to solve it, because we recognize that it is a limitation and it does limit us, and we just want to make sure that we're responsible so that we don't cause a whole lot of undue burden. Like, we don't want to bankrupt companies by basically accidentally killing their business off. That would be a really bad thing. And so we try to go slow with it.
So my point is, I think companies, sometimes I think is that these big companies are people that do business using technology. They are not aware of this, and when they are building business, they don't put it in the table, for example. And I think it's really important. That's what I'm saying. We need to change the narrative of using technology. We need to stop assuming that thing will be forever. We need to start assuming that in order actually to for example, you can say, oh, if I break my code, right, for example, and call a new team, maybe we can have maybe we can just have a more organized way actually to update code when the architecture break it, right? So that the user cannot feel it. Maybe you start research in that direction also. That's what I think it's a direction to do research, for example. But now, ignoring that, sometimes we need to break dependencies, we need to break backward compatibility. Is not good for anyone, because even if you have your business, your language, your compiler, for example, the architecture that you use, well, you're not making the best of these, right? Your users are not happy. They keep in the same, I would say, the performance is not changing, for example. But now you can see that there is a people that using these new features that the hardware is providing, they break compatibility, and now the users are happy because they have a more optimal execution of the softwares that they get from you, for example, or from another provider. So I think it's time really to change. I think it's a mindset that needs to change. I think that people, when breaking the table, oh, let's break compatibility, it's like people start looking at you like, oh, maybe you're crazy or something like that because of business. That's the mindset that needs to change, I believe. We need to change that. We need to think like it is important for the evolution of software. It's important if we want to keep providing high quality of our products in terms of performance, and make a better use of the resources that the hardware or the compiler techniques that are available to use now. So
yeah. I definitely agree the mindset needs to change. Whether or not anybody's capable of making that, driving that change is the part that's really, I think it's suspect. But I think we'll find technological solutions to this that will actually help. So as a good example, GCC has an attribute called ABI tag. And this allows you to basically say, here's a definition of something. It's got ABI version 1. Here's the same definition of the thing. It's ABI version 2. And now you have a way to basically version the binary interface. And so you can continue to support people who need the V1 with the extra expense of your binary being larger, because now it has 2 copies of the same sort of thing in it. So there are some technological things that we can do to try and make this easier. And I agree with you that it would be great if we could find a way to change a mindset. But I've been really surprised by how many companies actually don't care about performance. My software works, my users are happy, it makes me money. It's not a product I sell, it's an internal app or whatever. And they don't care about the performance always. But there's a whole lot that do. And so, how do we make sure that everybody's happy is always a hard thing.
Yeah, because this mindset actually, of course, you said, for example, the company doesn't care. For example, think about people maintaining x86 microarchitecture, for example, the instructions, the x86 architecture, for example. The backwards, for I don't know how long it is, for example. Anytime Intel wants to update, it's so complex. For example, they still need to provide the support for the support for backward compatibility, and it's make the life of the engineer hard, right? And it's backward compatibility, something that always need to be put in the table when making decisions. And I think it's not okay. And it's need to change, and we need to find a way to get rid of this problem in a way that we can make both the engineers and the business people happy. Or at least reduce the burden a little bit on these people engineering, for example, because it makes it hard. For example, for someone trying to build new feature for C++, he need to look at the language from I don't know how many years ago, because there is things that, and it is.
Yeah, I largely agree. I'd say I doubt we're going to make everyone happy, but I suspect we can make everyone equally sad, and that's just as good.
So we have a question here. So what are your thoughts on Rust borrow checker?
So it's interesting that you bring this up. This has been coming up in the C standards committee an awful lot. The C committee has been looking into, they've been exploring adding some sort of idea of a safe C subset. So there's a C and then there's a C without UB kind of idea. And they have no idea how this is going to happen. And so the borrow checker and Rust in particular just come up an awful lot. One of the challenges from it in terms of the C and C++ is the Rust borrow checker really, as I understand it at least, requires the compiler to be able to track ownership of a pointer. To know, have I borrowed the ownership of this pointer, or have I not borrowed the ownership of the pointer? And the big problem in C and C++ is we don't have any way of getting that answer because we don't see all the translation units in the program. And so it's more than likely going to be that in order to have something similar, we need to come up with a different syntax to basically have, there's pointers and then there's owned pointers. And so with the owned pointer syntax, maybe instead of using a star to designate it, it uses a caret or a hat or whatever. We come up with a different syntax that we can then assign different semantics to, that we could then build up kind of the model on top of. I think that might be more likely, but that's also much more explorative than I think C is usually used to going. And so I don't know that we'll end up getting anything similar to this until compiler implementers start playing around and seeing what works with people. But it's in terms of the borrow checker itself, I like the concept. I'm just not certain it's ever going to come over to C++ or C.
Yeah, we have another question. Is Intel has a DP++ compiler based on LLVM? What do you think about Cycle, and are there any plans to bring that to Clang?
Yeah, so this is something that Intel is actively working on. And there's a bunch of us who do work on Sickle, and it is something that we are trying to upstream into Clang. We're pretty far away from it being upstreamed because it's a large change to the programming model, and it's a large library to come along with it. So I wouldn't say that Clank is going to be usable for Sickle anytime soon, but the plan is to get it there. And so that's the hope. In terms of Sickle itself, I think it's a really interesting technology. It's interesting in that it's in the same design space as a whole lot of other stuff. So OpenMP and CUDA and stuff, like OpenCL, like a lot of these things are all in that same sort of design space. And so it's interesting from that perspective to see how it differs from the different technologies and which places it's like, oh, this is easier in Sickle and it's harder in CUDA and impossible in OpenMP or whatever it might be. And trying to figure out like what's, from a language person perspective, what is it that, how to phrase it? Sickle's interesting just because it's one of those things where we can kind of see where the good ideas are and try and take good ideas from other technologies and see what happens if we put them all together in one place. And whether or not that ends up being successful or not, I think is a little unclear, but it's nice to see that people are still designing new things in the space and trying to make GPU programming, general GPU programming much more accessible to people.
Yeah. I think that there is. I think this idea of Cycle bring up some thoughts that I have on the way we are providing support today for writing high performance programming, for example. And the barn is more in the programming today, because Psycho is maybe a good technology, but what about using it, right? Be it to an average programmer, how it will succeed, for example. You have different technology you have different, I would say, functional, I would say is different execution, I will not say execution unit, different agent inside of your processor. For example, you have GPUs, you have CPUs, and today we are having DPUs, that DRAM processing units, for example, and you have all of them, right? So now how you write your code in a way that all of them can share data, for example. And you may have, for example, that, okay, for the first 10 minutes of your program, the codes that you have need to be executed on a GPU. After that, the GPU need to pass the data, because for after this 10 minutes or seconds, now the CPU need to take and execute, because now the presence on the data change, or the task you want to execute change, and so on. So I think the idea is not actually only good to put all things together is something, but actually the most important one is to provide an interface that can be that is easy to use, and that's something that, unfortunately, I don't think Psycho provides it. I think not average person can use Psycho, and I think this is the real downside of Psycho.
Yeah, and I'm in the same boat in that I'm a compiler developer. I don't want to go learn all these GPU technologies to take advantage of it. I would just like my compiler to do that for me. And I think that's a good goal to get to. And part of the problem is that we kind of have to experiment with different things to see what works and what resonates with programmers and what doesn't resonate with programmers. And so I think we see a lot of experimentation in this area because the hardware is changing so fast. And I think everybody recognizes this is kind of the future of computing. So we'll get there eventually, but there'll be bumps along the way.
Yeah, I don't think it's going to change in the point. I think the direction of computer architects and labs today is actually now the design is across the stack. Now, sometimes it was okay, let's go on to the compiler. Let's talk to the compiler. Now it's not only the compiler. We need to talk to the user, right?
Yeah.
For example, there's a lot of proposals that ask, hey, do you know your data? Do you know the pattern of your data? For example, I was even today reading this paper. It's really a nice paper proposing a new block interface for virtual memory, for example. And now you need to provide your operating system with information. For example, this particular code here is a data structure. I need to transmit your memory controller in order to understand, now this is a data structure. Maybe I have this pattern. This is maybe the memory controller can use this information in order to provide a more efficient, to provide a more efficient service, for example, to your program, for example. So now people are designing things that you involve the programmer. For example, you need to specify this. For example, we talk about attributes, right? Like unlikely and others. Now we are touching the program. You need to inform. You need to talk now. So, and I think going forward, this direction will not change. And I think it's not change today because it is maybe if we change the paradigms to gain performance. I mean, the hardware at large. When people say, hardware is getting fast, hardware is not getting fast. Hardware is giving up to be general, to be specific, for example. And that's why there's also a lot of opportunity on. That's why there's a lot of opportunity on compiler, because now, for different data, for different workload, it may require a new target, for example, right? Today we have AI accelerators, for example. They may require their own compilers, for example, to target particular hardware, because now in this target is well optimized for AI. For example, we have TPUs from Google's, we have systolic arrays, for example. And these are examples that I think it's the golden age for computer architects. It's also the golden age for compilers, for example. And I think it's exciting times to go ahead. So I think, and in my point of view, programming will be harder going forward, really hard. Because if you're trying for performance, it's really going to be hard, because the way people are trying to provide performance today is really exposing things to programmers, for example, right? If you're going to use these likely and unlikely C++ attributes, you need to understand you are talking to the branch predictor inside of your pipeline. Hey, branch predictor, don't do your speculation, right? You'll be wrong. I know the behavior of this program is too crazy, and don't do that, right? Maybe just trust me. This is taken 99% of the time. Well, the another problem is if you're wrong, right? The hardware will cost you forever.
Oh yeah. Yeah, no, that's always the challenge with a lot of those attributes too, because you'll add them into your code and you're like, oh cool, I want to inline everything. That must be faster. And it's like, no, not what you would expect.
Yeah, and I think we can move to another stage of the talk. We still have size. I think we stop it here because you went questions.
Sure. Oh, I don't mind questions. You can stop me anytime.
Okay.
So just moving on to C and C++ standards. So I just wanted to talk a little bit like how do programming languages spring into existence? Where do they come from? And in terms of C and C++, they're both ISO standards, but there are other standards bodies, and there's nothing wrong with them. And that doesn't mean that ISO is great and the others are bad. ECMA is one that's used for JavaScript and C#. IEEE defines what floating point values look like. So there's a whole lot of different standards, and they tend to interact with one another. So for a good example, C and C++ reference IEEE standard for floating point, and they reference the Unicode standard for Unicode and that sort of thing. But a programming language doesn't actually need to be standardized, and that's fine too. So there are programming languages out there for which there's a reference implementation, and that's it. Documentation. Python works that way. There's no standard for Python. It's just, that's what it is. It is what it's defined to be. Perl is the same way also. And so, there's different approaches to standardization, and C and C++ decided to go with ISO back in the mists of time, along with COBOL and Fortran. I think are the four big ones that ISO standardizes. But these committees they're separate. You would think that C and C++ committees would actually be one committee because C++ relies on C for so much of what it does, but they're actually completely separate standards bodies, and they're completely separate approaches to how things get standardized.
And I have a particular question about C and C++.
Sure.
For example, I have a book, and the name of this book is Inside the C++ Object Model. It's a great book, really. It was great from one of the, I think he was a maintainer of the C front. I think it was the front end for C++ back in the times. And reading this book is really an amazing book, right? Because this book is really about the data. And important thing to see in this book, what I was reading and really trying to put my mind inside of the book to extract the mind of the author, as I kind of see that C++ exists at maybe I'm talking about the C++ in this book because the book is really old, even though many of the things still current, because I looked at the assembly code and I read and I say, well, the translation is still equal. I don't know what's happened in the front end to get the translation, but what I have here is what he's explaining actually, even though the book is old. But the important things, I see that if C++ has some features that are implemented exist in the language, right? It's not a Libre feature, but it's really in a way the user to communicate the compiler in how it should translate the code. But there is most of the codes and most of the idea in C++ can really be implemented just using C, for example. And I saw that C++, most of the C++ you have today, for example, the different paradigms that we have in C++, for example, they're just using the building blocks that the C language provide in order to provide this. For example, object-oriented programming in C++ are implemented using C building blocks. I'm saying pointers, for example. If you don't have pointer, you cannot have object-oriented programming in C++. And it's bringing me the idea that, well, the compiler, while compiling, it translate the C++ into C, and the backend part takes the C and translates it. So it's kind of an idea that I have, for example. I said, like, the C++ exists unto compiler time, unto certain time in the compiler time, because the compiler will destroy the C++, translate into a more, something like, maybe look like more like C, and then translate it to the hardware, for example.
And that's how compilers That's how early compilers actually worked for C. For C++. So if I recall correctly, even C front worked that way. It would just compile down to C, and then you'd pass the C onto the C compiler, and it would take it the rest of the way. I think it was around C++ 11 was really when that stopped being plausible to do. It's not that you can't get C++ to output to C. It's that the C you get out of it is really not C that you want to try to get optimized. It gets really complicated really fast. When you think about things like lambdas and templates and generic programming and that sort of stuff, sure, it's possible to do in C. Even function overloading, you can emulate it in C if you want, but it's not a trivial thing. And so I think as an implementation strategy, that's kind of largely gone away. And it's partially gone away because it turns out that in terms of language itself, C and C++ are different languages, even if you're just working in the C subset within C++. So the inline keyword in C++ is different than the inline keyword in C. Sorry, didn't mean for that to happen, but that's kind of what happened. Atomics is another good example. Sometimes the atomic stuff is different in C and C++, and we try to unify these things as much as we can. But I actually sat down and started coming up with a document that I affectionately titled C XOR C++ programming. It's code that is the same in either language, but you get different results depending on whether you compile it in C code or C++ mode. And it's up to like 20 pages of examples. So trying to implement a C++ compiler by doing it as a C compiler translation, you'll get something C++-ish, but it probably won't be conforming C++. And so it's tough. It's actually shockingly easier just to do the C++ compilation directly.
Yeah. So yes, another question is compiler principles, techniques, and tools. Do you recommend this book to learn compilers?
Let me look that up to make sure that's the one that I'm thinking of.
The Dragon book. I think it's the Dragon book.
Yes, I thought it was the Dragon book. That's what yes, I do like that one. It is a good book. That's one that I've got on my shelf in a different room. Well, I knew it sounded super familiar.
Yeah, but now people today are saying that, I mean, most people, for example, when I was buying books about compilers, you can see here, I have maybe, I don't know how many books on compilers, maybe 7 or something like, and the most recommended books today is the engineering compilers, actually. But many people today are proposing. Yeah, and then there is engineering compilers, I think, is the book by most people today is offered, because they said that the Dragon book's okay, but it focuses a lot maybe on, I think, in Lexing.
Yeah.
Yeah, and yeah, you can continue, please.
Oh, I said, from what I recall of the Dragon book when I was reading it, I was doing the second edition, which was the one with the purple dragon, not the red dragon. That one, it was good, but it was describing compiler technology that seemed to be a little bit out of date in terms of where the state of the art had moved to on things. And so it was good for teaching kind of the basic concepts of things, but it wasn't something that you would use to sit down and construct necessarily a modern compiler from, but you could. But I would recommend reading them both. Read as many books as you would like to read on the topic. Thank you for the recommendation, Felipe. That was good to know.
There is this book. Many people today recommend this book. And another question that I have is, if there isn't a book resource that you recommend people to read, to use in order to start contributing to Clang?
I don't know of any books that are focused on the topic of how to contribute to Clang.
No, maybe that one can read, understand, so that you can help him to start contributing to Clang.
Yeah, so I was going to say what we do have is we have a compiler internals link. Let me find that documentation. Here we go, and I will see if I can figure out how to copy and paste this into the chat. Hopefully people are able to see that. If not, you can search on your favorite search engine for Clang internals manual, and it should get you to where you want to go. But we basically have some documentation that describes at a high level the concepts that are within Clang and kind of the architecture of the project. I'm not going to lie, it's open source documentation, so your mileage may vary in terms of how useful you find it. But if it's a good starting place to try and figure out just the high level details of how Clang works. And the Clang community has a mailing list. CFE-dev is their mailing list that you can get to from the Clang's website. And asking questions on CFE-dev will get you a lot of help from people when you want to try stuff out. And that's basically how I got started, was looking at the internals manual and just asking other people in the community. And so anybody who's watching and is like, oh, I'd like to try something out and I have a question about Clang, feel free to email me. I don't mind getting emails from folks. So my email is aaron@aaronballman.com. And feel free to just say, hey, how's this working? And if you decide you want to try writing a patch and you don't know who to have as a reviewer for your patch, add me. I'll find the right person. So I'm more than happy to help you out.
Yeah. So I think we can continue.
Okay.
We don't have more questions.
So these two committees, C and C++, are actually shockingly different in terms of how they work, and just how they're comprised. So C++ committee is called WG21 because ISO loves putting codes and acronyms behind absolutely everything. But it's the C++ committee, and there's about 300 people who are in this committee. So it's a very large group of people, and C++ is okay with invention. So if you can dream up a really good idea and you can convince 300 people that it's a really good idea and that it's a sound decision, then we'll go ahead and accept it, and we'll try it out and give it a shot and see how it works as a standard. And sometimes this works out great, and other times not so much. And we all have our favorite features that just kind of fell by the wayside. But one of the things that C++ does to mitigate this is it has shorter release cycles. So every 3 years, we try to release a new standard, and we've been doing that since C++ 11. And this allows us to kind of correct things as we need to, but it also allows us to go, hey, if it's not quite ready for this ship vehicle, there's another one right around the corner in just a couple of years. So if it needs to bump from C++ 23 to C++ 26, who cares? It's not the end of the world. And so it's kind of our way to try and help make sure that we're producing a quality product. But the way the C++ committee tends to work is we have full week-long meetings that are split up into about 20 different rooms of people. So we've got work groups that focus on evolving the language and evolving the library. We've got work groups that focus on writing the words for the standard based on the intent that they get from the evolution groups. And we have a whole pile of study groups that are just looking at very specific topics. So we'll have a study group on concurrency. We'll have a study group on undefined behavior. And we have a study group on C and C++ compatibility. And so what will happen is people will basically submit their papers, and they kind of bounce around to all these different study groups as they're relevant before eventually getting into the evolutionary working groups and saying, oh yeah, nope, that is a good idea. Now that we've pounded out a lot of the details of the individual topics, does this make a lot of sense? And if evolution says, yeah, that makes a lot of sense, it'll move on to a wording group to go, okay, how do we turn that intent into words in the standard? And during the pandemic, the way the C++ committee has worked is we just have continual virtual meetings. I would say last month, I think there were 3 days that did not have a WG21 meeting on them at some point in time. And so they're usually just an hour or two here or there for any one of these particular group sets of interest to you. And so almost nobody tries to track the entirety of C++. It's just not possible to do. Usually what we tend to do is we focus and specialize on the areas of expertise that we have. And so we'll go to the particular study group meetings that are we can add a lot of value to, or the evolutionary work group or wording work group as you see fit. And that's worked out fairly well for us, but it's also been an interesting challenge because it means that it's harder to keep track of all of the changes that are going into C++, because we're no longer all together for 1 week where we have hallway discussions and we hear, oh, this was discussed over here, and then lunchtime discussions and dinner discussions and that sort of thing. And so C++ 23 is likely to be more of an incremental change over C++ 20 than a revolutionary change over C++ 20, which is perfectly fine because C++ 26 is just around the corner, and that's when we'll get, more evolutionary things.
And another question that I have how do you see the future of C and C++ programming language?
Not certain I understand the question.
For you, what's the future of C++ and C programming language?
Oh, like what's the big features that are coming up?
No, the future.
Oh, the future.
Yeah. For C and C++.
I think so. It depends on when you ask me. So I think the future for C++ is really interesting. And I think we're kind of, C++ is evolving really fast. And it's a really interesting kind of experiment because, you have 300 people who are evolving this language. And it's not like there's 1 or 2 people with a grand vision that are trying to make sure that everything fits just right. Instead, it's 300 people all moving in different directions with different goals and trying to come up with a coherent product. And I think that's something that's easier to do when the committee was small. When it was like 50, 60 people, I think it was easier to make sure that even though everyone's heading in somewhat different directions, they kind of line up a little bit. And with 300 people, it's sometimes harder to make sure that everybody's aligned in the same way. And so I'm curious to see how C++ evolves in the future and whether we're able to keep up the pace of new features with so many people trying to move in their particular direction. On the C side of things, it's a little bit different in that I think C has to try and figure out what we want to do. Do we want C to be a language that doesn't change very much and is kind of ossified into whatever C is, and we just fix things, but we don't add big new revolutionary things to it? Or whether we want C to be a bit more modern, I guess, really, and try to do new things. Should C get lambdas is a question that's coming up in the C committee currently. And it's, there's people who think, well, if you want lambdas, they're in C++, go use C++. And there's other people that are like, well, C really would be much more powerful if it had lambdas. And so I think with the C committee, it's more an existential threat of what does the C committee want to do, and with the C++ committee, it's what are we capable of doing.
I see that the C++ programming language going in the future will be really a point where any system programming language we need to look in order to learn how to build, because I think it's a very rich source of ideas and implementation, and even in the process of implementing and evoluting a programming language. And I think it's really important, I would say, for the other language in order to avoid repeating the same mistakes. But for C, I don't know for which reason the C programming language is not changing. So can you explain why C refuses to change?
Yeah, actually, thank you for bringing that up, because I can go to my next slide. So the C committee, by comparison, is about 30 people. So it's a tenth of the size of the C++ committee. And we actually grew over the pandemic. So we grew by almost 40% during the pandemic, because we started having virtual meetings where people are able to attend from wherever they are in the world, and you didn't have to try and have your employers supporting your travel. But one of the big things with the C committee is their big focus is we value existing practice and we value not breaking existing code. And so what I mean by that is the way that C adopts new features, unlike C++, we don't do invention in C. So in C++, if no one's implemented it, we'll still give it a shot and see how well it works, because we've got enough experts looking at it that we can really convince ourselves that we like the idea and we think it's a viable solution. Whereas with the C committee and the number of people that we have on the committee, it's a lot harder to feel that you have enough expertise for a language that's used by as many people as C to be inventive. And so instead, what we say is you have to get your idea implemented by not one, but two compilers. And so if you want to, if you want something in C, you've got to convince at least two of the C compiler vendors to give it a shot. And that gives us implementation experience where we know the feature is actually implementable, but more importantly, it gets us user experience where they say, we really like these aspects of the feature, but this little bit over here is terrible. Please don't do that. And sorry, go ahead.
It's not the idea of the TS in C++.
It's so both C and C++ have technical specifications for TSs, and that is for a lot of the more experimental stuff. And C++ has used the TS process a bit more than C has, but it's been a really interesting process. Personally, as a person who works on compilers, I find the library technical specifications perfect. Love them. Things like library fundamentals, TS, and those sort of things are great because it gives us an opportunity to kind of experiment with library interfaces and see how they work before we finally, finalize the interface and say, this is never going to change. In terms of language features, it's a much harder sell because language features are really expensive to implement. And if it's an experiment, companies tend to go, we'll see who does this first. And so you wind up in the situation where the people who have the most financial resources to do the experiments all have cold feet and go, I'd rather see somebody else take that risk. And so it's hard to get as the same kind of experience out of that technical specification for language features. And so I don't know. I think some have been successful and I think some have been less successful. So as a good example, I think modules wasn't nearly as successful as we were hoping it would be because, we put out a technical specification, we got a whole bunch of feedback from it, we made some changes to it, but there was still quite a bit of implementer disagreement on what modules should be. And the modules landscape is, kind of as a result, a little bit of a mess right now. And we're all still trying to get it into shape so that we all implement what the standard says. But it wasn't a slam dunk. It wasn't, we got the implementation experience and it all looks great. Everybody who implemented that TS had to change, and that's expensive. So it's a good process, and I love the theory behind it, but it's hard in practice, depending on what the TS is talking about. And I think the C committee is going to be learning this. We have a technical specification that we're putting out that we're in the process of working on right now, because we're trying to basically define what the C memory and object model is. It turns out that when you read the C standard, it gives you a lot of really good ideas about what the memory and object model of C is, but it doesn't really specify it very well. And so everybody does things a little different. And so you have a whole lot of problems where pointer provenance works differently depending on who implements it. And can you do type punning through a union, or can you do type punning through memcopy, or can you just use casts? Like those sorts of questions are not really clearly answered. And so the C committee is going, okay, we're going to come up with a technical specification that says, here's all the possible ways that we could answer every one of these ambiguous questions. What do you think we should do? And the study group has come up with, here's our recommendation of how we would choose these options. Will you please go out as compiler implementers, change your compilers, and see how well this works? And I think that change your compilers and see how well this works part is going to be the really tricky part of this technical specification. But it's great that, the committee's at least trying to solve some of these problems, because that is one of the big areas of C that is difficult to know. Have I hit undefined behavior or not? Shouldn't really be a question that you have to think about too hard. It should be more obvious.
And the other question is why the C commit is too small comparing to C++.
So the C committee has gone all over the place. When C89 was standardized in ISO, from what I recall hearing, I wasn't around for this. It predates me caring about programming because I was like 10 when this happened. But I think it was like 200 people on the C committee at that time. And what happened is over the years, the C committee, they do TikTok release cycles. So they'll have C99 came out and it had a whole bunch of new features in it. And then C11 came out and it had some new features in it. But then C17 came out and that was basically just bug fixes. And so there can be a long delay between when you're starting new feature work and when you're not. And I think that a lot of people they lost interest. They didn't want to join the committee just to fix bugs because that's not the exciting work. And so I think we lost quite a few people, and we're starting to build our numbers back up again. And I think C99 hurt us because we were inventive. We invented a whole bunch of things in C99, and most of them worked out okay, but some of them we had to roll back. So like variable length arrays, they were required in C99 and they became optional in C11 because it turns out there were computer architectures for which that just wouldn't work. tgmath.h was not something you could implement in C. We'd standardize it in C99, but you needed compiler magic in order for it to work. And so in C11, we had to fix that by making this underbar generic monstrosity to allow you to do somewhat akin to generic programming in C. And so I think some of those sort of things scared people off from the C committee, but now we're seeing kind of a resurgence in interest, which has been fantastic. And a lot of the interest has actually been coming from C++ members who are starting to recognize that C++ can't exist without C. Operating systems typically don't ship C++ headers for their OS APIs. They ship C headers. And if the C programming language were to ignore C++ entirely and evolve in its own direction, we could run into a situation where operating systems start giving interfaces that C++ can't recognize. It uses a different syntax. Like imagine if we changed what a pointer looks like. If C++ didn't do that at the same time, none of those C interfaces and POSIX and the Linux headers and the Windows headers, like if they started using that new syntax, you couldn't use it from C++. And that would be a big problem. And so we're seeing a lot of C++ members come over to C and say, okay, how do we responsibly make sure that these two languages don't drift too far apart? Like they're separate languages and they should be treated as separate languages, but they're still related. And we should make sure that we don't cause a lot of economic harm by ignoring the relationship between the two. And so that's been nice. Both the C committee and the C++ committee made a study group for compatibility with the other language. I'm the chair of that group, but it's been really interesting watching people who are, I only care about C, here's my thoughts. I only care about C++, here's my thoughts. And when they meet, they go, oh, well, that's, we thought we were going to be connecting right up, and it turns out we weren't. So there's been a lot of good benefit from that sort of collaboration between the committees. And I hope we continue to do that, because not only will it help the C committee continue to grow, but I think it'll help C++ avoid some problems.
Yeah.
So the thing to know about standards committee, though, at least in terms of C and C++, is this is everyday folks. We are not wizards on the C or C++ committee either. There is nobody who knows everything about C++ or C. They're both just too big for one person to go, oh yeah, I know absolutely everything about this. More often it's, I know absolutely everything about this one little tiny portion of the language, and then I know enough to be dangerous in the other parts. Nobody does this full time. It's not an all day, everyday sort of job. It's more, you get what you give. So you put in some effort, and your efforts will kind of increase over time as you're doing something interesting, and then they'll decrease over time as you're not doing something interesting, and kind of waves back and forth. Some folks do get corporate support in terms of just sending people physically to meetings and that sort of things. But surprisingly, I would probably guess the majority of people on both committees are volunteers where their company doesn't necessarily pay them to do this. So they write their papers on their own time, and maybe their company will help them with making sure that their dues are paid, or they might make sure that they get some sort of travel stipend or that sort of thing. But quite a few people are just on their own dime and on their own time doing this stuff. And some folks are long-term and other folks are just interested in one topic. So, we have some standards committee members who have been around for 25, 30 years, and they've got all this historical knowledge. And then there's some other people who I'm just interested in this one little bit. I want to make sure modules gets in, and that's all I'm interested in. And what's great is we love all these folks because, it takes a village really to make these languages work and to evolve these languages. And so whether you're doing long-term or short-term, and whether you're doing, you're getting corporate support or you're volunteering, we try to make space for everybody. And make sure that everybody gets heard exactly the same, because it's really important. And so on that note, anybody can join these committees, but unfortunately, because it's ISO, the process differs by country. And so some countries charge people to be a member of an ISO standards committee. Like in the US, you have to pay money to be a member of the ISO standards committee. And then ISO turns around and charges you to sell you the standard you wrote for them. It's kind of nuts, but it is what it is. And other countries, it's totally free to join. And so if you're interested in joining either one of these committees, you really have to kind of find out how your country does it from where you live in or where your employer is stationed in. But if you do have any sorts of troubles with it, and you're like, I'm curious and I have no idea where to start, feel free to email me. I have absolutely no idea what the process is for Angola. I'll find out.
Yeah.
But just like with software, standards also have bugs. So we're not perfect. We call them defect reports because we like to sound really officious, but they're bugs. And in C++, we're at about 2,500 defect reports, and there's about 500 in C. And that's just the ones that we're currently tracking. So, I mean, there's plenty more that we don't know about yet, and we'll learn about in the future, I'm sure. But as we work on these languages, we definitely do get bugs. And so the thing to know is you don't have to be perfect to be on a standards committee. You can be just enthusiastic and passionate about the topic, and you don't have to have a big professional background in doing compilers and programming languages. You can have literally no experience. The C++ committee had a high school student who came and successfully had one of their proposals proposed, and they saw it all the way through until it got shipped, I think in C++ 20, might have been 17 as well. But, that's not a person who's going to have a significant amount of compiler engineering experience, professional compiler engineering experience behind them. They're just passionate. And that's really what's important, is just being passionate and being willing to work with other folks. And so if you are interested in doing standards committee stuff, I would definitely recommend it. It's really an interesting process to go through. It also can be extraordinarily frustrating, just so you know, because the whole point to it is to have enough bureaucracy to stop ideas that might be contentious. And so it's a very conservative process to evolve the language typically. And so there's a lot of paperwork. There's a lot of making sure you get this filed on time, and then you've got to go to that meeting in order to discuss it, and then it moves over to here, and you need to know these rules. And you pick that stuff up as you go, and people on the committee kind of explain to you, like, okay, here's the next step for your paper. So we always give you enough feedback so that you know what you need to do next. But it can definitely be frustrating when you're like, well, I really would like to submit this feature to the C committee, but they're currently only working on defect reports. And so I can't, they're not even going to discuss my paper for the next 3 years or whatever it is. So it could be kind of frustrating in that regard, but it can also be extremely rewarding. And so with that, I'm wondering if people have questions about standards committees. Feel free to ask anything that's on your mind. And also feel free to enjoy the picture of Terabytes looking like a Mainer with her little flannel hat.
Yeah, I don't see here any question. I think we
Okay.
can go forward.
Sounds good. So what do you do if you're interested in this stuff and you'd like to get paid to do it? Some people like doing both compilers and standards work, but you should know that you're not required to do both. Many folks do one or the other. At least at Intel on the front end team, there's 2 of us who go to C++ standards committee meetings, and there's 2 of us who go to C standards committee meetings. And there's like 15 of us who work on the compiler. And so, the majority of people are working on the compiler and don't really care what's going on in the standards committee. They can just read the papers. And it doesn't need to be a long-term commitment to either one of these sorts of things, standards or compilers. Any amount of effort is really appreciated in both places. But you should know that it's harder to find corporate support for doing standards work than compilers. Companies tend to not like standards work simply because it takes years to see the results from the efforts that you're putting in. And so companies tend to be a little more short-sighted than that. They tend to like, can we see the results in the next 6 months sort of things, not can we see it in the next 6 years. And so it can be a little bit more difficult to find people doing standards work than compilers, but it is still possible. And the companies that do this sort of stuff can be really surprising. Hardware companies is a kind of obvious one. If you're working on hardware, you probably care about compilers. So Intel, IBM, Apple, ARM, all these sort of places, they do compilers and standards. And there's mixed software and hardware companies that do kind of a bit of both, like Microsoft and Sony and Samsung. And these ones are not all that terribly surprising. But other industries is kind of fascinating to me. Facebook, Bloomberg, Morgan Stanley, video game publishers, all these folks send people to standards committee meetings. The finance industry sends a lot of folks to standards committee meetings because they want to make sure that optimizations are preserved for their use cases. And it's the same sort of thing for video game publishers. They want to make sure their use cases are considered. And so you can actually find people hiring compiler and standards work in really kind of surprising locations. And so if you are interested in looking for careers in this sort of thing, keep an open mind in terms of what kinds of places you can go. And they can also be, tangentially related. It's not necessarily compilers. You could work for a static analysis company like Coverity or Grammatech or Clockwork. You're working on the same sorts of problems. You'll still be working on compiler front ends. You still have an opportunity to care about the things that are happening on standards committees. And so there are actually a surprising number of jobs in this industry. And I know that different companies are hiring right now. A lot of companies in tech are hiring in general, but just in terms of compiler stuff, people are hiring in these sorts of things. So if you're interested, go for it.
Yeah, it is, as I said already, this is a golden age for computer architecture. So it's because we have a bunch of new architecture because of the new workloads that we have today, and this workload people maybe build a specific hardware for this particular workload, so indeed requires also a compiler to compile to this specific machine. So I think it's an exciting time to get involved with compilers, for example. I like compilers too much. I really like them. I mean, sometimes building, sometimes just looking what they have my high level code, and I want to see what the general code that the compiler will come with. And sometimes it's surprising. You see, wow, the compiler is really good. And sometimes it's, oh, you can do better.
Oh, yes. Yeah. Compilerexplorer.com is definitely, I would say I spend half of any given workday in Compiler Explorer, just trying to see. I mean, I personally, I work on the front end side of things. And so for me, it's okay. Clang is doing whatever. It's accepting this code. It's rejecting this code. Well, what does GCC do? What does ICC do? What does MSVC do? Like, how do all the other compilers react to this sort of stuff? And It's a fascinating field. It's a great time to be in it. There's a lot of people doing back-end work. You'll find more back-end jobs than you will find front-end jobs, because to hardware companies, the back-end work is what makes them all their money. And so they're willing to spend money on hiring resources to make sure the back-end works really well for their architectures. And the front-end work tends to be a little bit harder. That's more of a standoff between all of the big companies saying, no, you implement this. No, you implement this. And so it tends to be, the front-end stuff tends to be a little bit easier to get into as an individual in some regards, because you can build up you can demonstrate to companies like, see, here's all the commits I made in Clang or GCC or whatever. I know what I'm doing. Do you want to hire me? And then they go, oh, okay, that's a great idea. So it's a little bit, you need a little bit more work sometimes to find the front end jobs, but they're really satisfying.
Yeah, talking about different compilers, actually, by experience, I also use Compiler Explorer a lot, especially when I'm studying C++. I place my codes in this Compiler Explorer, and I want to read the assembly code to know what the translation of this code. And you can change the compiler. You can see both compiling, sometimes implementing different solution. So, but another thing that is really important was I was reading my code that it was like a couple of months ago. I was using Compiler Explorer, and I saw that, so there is the C++, the x86 ABI, for example, and the ABI for calling functions. So the calling convention of x86. So the ADI parameter is the first one. So what happened is when you have a function, a normal function, and it's a normal function that is implemented in C++, you just put your parameters. What happened is, like, if you use a standard function, a function that belongs to the standard library of C++, well, what happened is the compiler need to take that instruction, because the calling convention says that you need to place the first parameter into the ADI registers. But what happened is you need to call the standard function inside of your function. So what happened is the compiler need to take the ADA parameter to pass to the second parameter in the calling convention, because the C++ standard, the first parameter is an address to call it. I don't know if it's I don't know why the compiler do that, but I noticed that this thing is wasting one instruction. Why? Because if the standard assumes that the parameter that is used to call the function, the standard function, is the last, you won't have this one instruction of moving the first parameter, in this case, to the second, so that now the second function needs to use the EDI. Well, the first parameters are the first for his. I don't know how to explain. It's so complicated because really it's hard to put into words. But what's happened is two functions need to obey the calling convention. Or the first one take the parameter that you want to pass to the standard that is inside of another function, right? Here is the first parameter, but the standard function have his own first parameter. Yep. So what you need to do, you need to make the value that you have that was passed to the normal function the second parameter to the standard library, because the standard library already have a first parameter that is a call. But if the standard assumes, for example, the compiler when translating the code assumes that, okay, the call parameter needs to be the last, so there is no need for that instruction, for example. And I think, like, I don't know why it happens. Why not assuming that the call parameter is the last when calling the standard, so you avoid this, so you avoid wasting one instruction and moving to respect the calling convention.
So the standard doesn't actually require the object that this pointer be the first parameter, if I recall correctly. I'm pretty sure they just leave it up to the implementation. They just say that the implementation is going to have the access to this pointer somehow, but they leave it up to the implementation to determine how that happens. And so my guess is first was just what happened because somebody thought it would work out great 30 years ago, and now that's just kind of become the convention, because once you've baked that into how you call member functions, now if you change it, you're going to break an ABI for all the people who can't change, can't recompile their code to change the parameter from being in the first position to being in the last position. And so it sometimes is a matter of practicality as to why these things happen. But a lot of times the standard tends to just go, I don't care how you do this. It's a quality of implementation thing. And so there's not necessarily a requirement there for it, but sometimes the requirement just comes from, if I were to change this to save that one instruction, I would break so much code that my users would come find me and hurt me.
Yeah, because actually changing this is breaking the ABI.
Yep.
If you make this parameter the last, you're breaking the ABI, and this is a big trouble.
Yeah. Well, and it's the sort of thing where it might also be that it's easier, if it's the first parameter, adding additional parameters on is easier than if it's the last parameter. Because if this pointer is the last parameter and someone goes and modifies the function, it changes all of the indexes. You can get weird behaviors from this sort of thing. And sometimes it's even surprising stuff, like the first parameter is, close enough on the stack that it's always going to be in the cache. And so if we put it there, it's great. But if you have a function that's got 35 parameters to it and we make this pointer the 36th, then all of a sudden it's terrible. And sometimes that's enough for people to go, oh, well, that's an important reason to make it the first one instead of the last one. I just assume the backend people will eke every ounce of performance out they can, though.
Yeah, but it's I mean, maybe I need even to study more to find more use cases when it really can affect performance, maybe. And I think it will be interesting. I actually noticed that, when I was reading, I said, wow, why it happens? And I was trying to use different, I was like, nah. Because I thought, like, okay, if you have this, for example, when we have this, I forgot the name of, we have functions that have variable length parameters. Functions actually assume to have variable length parameters. And the compiler was figured out, the compiler was figured out to get the last parameter, because the compiler is the one that needs to map, actually. Well, because how they only executes is all the work of the compiler to implement and to know the order in which you access the variables and so on. So if the compiler can figure out variable latency function, well, you can figure out the last parameter all the time. That's what I was assuming in the beginning.
Sure. Well, I mean, the fact that you noticed here's an instruction that we can save, that's the really important thing, because it's like, as a user, you shouldn't be responsible for solving that problem. You can just tell us, hey, by the way, I happen to notice this could be more efficient. Can you do something about it? And the people who have the ability to do a lot of measurements on stuff and go, okay, when I run it over a corpus of 400 million lines of code, here's the actual impact one way or the other. And it's always surprising to me. I don't have the patience for doing back-end work.
For me, everything is interesting.
That's great.
Yeah, but I think that the front-end part of the compiler is really beautiful. That parsing is beautiful. Lexing, parsing, it's really interesting too. I mean, it's really exciting topics. The whole compiling topic is really exciting. I remember my teacher of compiler, when teaching compiler, he used to come in the class and say, if you're not patient about this thing, you just give up computer science. He was coming to class and he was say, okay, well, if you don't feel patient for that, with what I'm explaining, and he was really passionate about compiling. He was an engineer at IBM, and still actually at my university, he was really passionate, right? You can see his slide. You can see the love for compilers in everything. It was one coming to us, oh, you should do all these courses, and he wrote books, and he's a really, really passionate person about compilers, and the way he teaches, wow, it was a very passionate person. And I think compiler is really, really, really beautiful. And the book that I just said, Engineering Compilers, there is one beautiful phrase that actually touched me when I was reading this book, is that compiler is in a field in computer science that almost touch everything else, right? It's like you take everything together in one piece of software that you need to take in consideration. And I found it to be beautiful.
Yeah, I love working in compilers, and I never thought that I would. But it's as we had mentioned earlier before. My big thing that I think is most enjoyable out of compilers is finding ways to alert programmers about the problems in their code before they get too far out of hand, where they go and release it to users. And so to me, there's nothing better than a beautifully written error message or warning message. So yeah, I hope other people find some compassion or some passion in compilers and programming languages. So as always, if anybody has questions, feel free to shoot me off an email, and I'm happy to talk shop about it at any point in time with any person. So
Yeah, you touch on a very important topic, that is finding bugs and mistakes, and it's really crucial in computer science in general. And both people and hardware today, there is a lot of focus today in security and safety and reliability. And the question that I have to you is, how do you deal with bugs? For example, compiler bugs, for example. For example, how is the, for example, compile is critical? Well, because now if you find that there is a bug, well, at the time you're solving, there's people compiling and using the version of the compiler that have the bug.
Yeah. So a lot of times the bugs, it depends an awful lot on the bug. So if it's a crashing bug, the way in which you solve that is very different than if it's a diagnostic issue where you're accepting invalid code or rejecting valid code. Crashing bugs tend to be a little bit easier because that's always a mistake. The compiler should either be accepting the code or it should be giving you a diagnostic. It should not be crashing and dying. And so finding and fixing those sorts of bugs is a little bit less scary because no one's ever going to complain that their compiler stopped crashing. No one within reason is going to complain that their compiler stopped crashing. But in terms of things like rejecting valid code or accepting invalid code, those are a bit more difficult because sometimes, especially like accepting invalid code, if it's in an area that's just a real edge case, a real corner case, and you're looking at it and you're like, wow, this should really only impact like 2 or 3 people, you can fix that bug, and you put in a release note that says, I've changed the behavior here. Really sorry if this impacted you, but your code was wrong before. Sorry. It's not such a big deal. But sometimes it's like, oops, it turns out that one line, it is only used once in libc++. It's like you can't just start rejecting everyone's libc++. Like that would not, or libstud C++, it just wouldn't work. And so you sometimes need to do basically compiler hacks. So as a good, for example, we have quite a few compiler hacks for the different standard library headers where the standard library was accepted. Let me try and come up with a concrete example. So Visual Studio might accept some sort of code inside of the Visual Studio STL headers. And so from their user's perspective, all the code compiles fine. And then you go and you use Clang to compile against the Visual Studio headers, and they start getting errors inside of Visual Studio's STL headers. And users can't change that. And so what we'll do is we'll go, okay, when you're compiling the code, we might take a look at the thing, and before issuing an error, we might say, is this inside of a system header? Is that system header named tuple? Okay, I'm just going to ignore this problem and not report it as an error and compile and continue to accept the code. And so in this way that we can kind of control a little bit where it's like we're making it so we're not breaking everybody who's using the Visual Studio STL, but we're still not necessarily accepting that code construct. We're only accepting it in this very limited, tiny case. So it's a balancing act between doing the right thing as far as the language is concerned and doing the right thing as far as real people who have to use your tool are concerned. And it can be, it's a challenge. Sometimes you get it right and sometimes you get it wrong.
Yeah, but I think another thing that I found to be challenging is the way, for example, if I'm building a software and I have a set of clients, I have their contact, and there is a bug I found. Well, the system didn't crash yet, but I know that in the future it will. Well, I have a way to contact them, but they need to update. Right?
Yeah.
The compiler and hardware is different, right? You sell your stuff everywhere. You don't keep contact with everyone. So when you find a critical bug in compiler, how do you communicate it? It's how you send alert that everyone needs to update.
So
Well, because things
yeah,
can get hard.
yeah, usually what we try to do is instead of breaking their code right up front and being kind of rude about it, just being like, you need to change. A lot of times what we'll try to do is give the user a warning. So we'll say, okay, in Clang 13, this code construct is going to give you a deprecated warning. And then in Clang 15, we're going to go and remove that functionality. And so anybody who is, still keeping up with Clang releases will hopefully have seen that diagnostic in some form or fashion and gone and modified their code. And if they haven't, well, we tried our best. So, if we can get away with that sort of thing, that's what we prefer to do, because we really do. We love our users, and we want to make sure that our users are happy, because if your users aren't happy, you won't have them, and there's really no point to having your tool. But release notes is another way that we'll use it. So for things we can't give warnings about.
Yeah, I found out, for example, operating systems that they have a much better way to communicate to users. Okay, update, there is a bug, because it's visible. You can interact directly in the system with the user, well, because they can get a sign of notify. Oh, there is a new release and you should do it. Well, with compiler, it's different, right? The user need to go to the website and see if there is new release or not. So if they don't do that, so there's a trouble, and you can not have a way to provide to how can I say to alert them that the code, that the current version of the compiler code they have may be buggy. So
yeah, no, and that's one of the things that so what I usually try to do is I try to tell users, assume that when you change your compiler, either switching from one compiler to another, or getting a new version of a compiler, or changing the standard flags in your compiler, you have a new program. You are going to have to retest this. I'm very sorry, but the compiler technology, you should just assume new compiler means you're going to have to retest all of your assumptions, because you're right, things could change, and they do. They change rather rapidly in compilers, and so you when you go to upgrade, you shouldn't assume that it's just going to be, oh, I've upgraded and everything should be exactly the same, because hopefully your code is actually faster and smaller and better with the new upgrades. It is changed, but sometimes those changes are also, now your code is wronger. Sorry.
Yeah, we have one question here. It's very important to study formal language and automata to be better in working with compilers, or can I put only hands-on compilers?
Hands-on compilers is great. I have no background in formal languages whatsoever. My background was in video games. I had one compiler class in college before I started at a compiler company, and I hated that class. In fact, I distinctly recall saying, who would ever need to know this nonsense? This is something that only 4 people in the world are ever going to get a job doing, and it's not going to be me. And that took all of 6 months later, and I'm working at a compiler company. So hands-on is definitely perfectly fine. Having some sort of formal background can help, certainly, but truthfully, a lot of it's just reading and reading and reading and reading. So a lot of times it's reading the standard, which is kind of impenetrable, and trying to understand what it's saying. And a lot of times that involves quite a bit of discussion to make sure that everybody agrees that we're reading it the same way. And then once you have an understanding of what the model is for how that should behave, a lot of times it's a simple matter of code after that. So you don't necessarily need a formal language and kind of automation and that sort of stuff to go around it.
No, that was our last question.
Great.
I'm not seeing more. Oh, okay. So, Aaron, thank you very much for being here with us today. I think it was a really, really, really exciting conversation, at least for me. I really enjoyed it a lot. It's an exciting topic. Compilers it's really good to know more about compiler and talking with someone with full experience in this field. And that's work on one of the most popular, I would say, compilers in the world, that's Clang. And thank you again for being with us.
Oh, thank you for having me. It was a lot of fun. It was, and I'm just hoping that people are like, hey, you know what? I can do this too. If you're interested in it, go for it, because it can be a really awesome experience to go see. I have changed the compiler and now my code does something different. Like there's a lot of power in that. So
Yeah, I think actually recently I started getting more involved. I was kind of co-author of the work that was done by Nicola Jesus. He was working on this range-based for loop and stuff. Well, when he made a proposal, and I was kind of co-author of the proposal, and then the committee didn't accept the proposal because they said that they were more, I think, long-term solution from the problem. And you are someone that worked in a committee. I know it is, there is two sides, and I think the committee always need to take the side in where what's better for the language, right? But when someone puts a lot of work, right, in a proposal that takes months, takes a lot of attention, a lot of energy, you kind of feel that sometimes the committee just rejecting a paper that, I don't even know how to put it in the good words, because I don't want to hear someone saying that the committee need to accept the paper of everyone. I'm not advocating for that, but I'm just trying to find a way, or a balanced way to trying to say, is sometimes the committee actually rejecting a really nice proposal that, and I know for people and that are really expert on the language, that know a lot of that know a lot of in the language, that have the ability to actually make a big contribution in the language, and they see the work that they put a lot of energy just being rejected. I think it can sometimes demotivate these people from keep working in the language, and I think it's a great loss from the community. So how do you think is a better way of dealing with this problem?
Yeah, so I know what paper you're talking about, and I was also disappointed that the committee was like, "Yeah, let's try to solve a different problem." It's not to say that the committee necessarily made the wrong decision, but it is to say I can see exactly why that's demotivating. I've been on the receiving end of that sort of thing as well, in both committees, where it's like, here's my idea, and even though I'm a long-standing committee member, it's like, no, Aaron, go away. All right.
Yeah, I think that's okay.
But one of the things that I find works really well with a committee is the way that both of these committees work is there's a status quo of this is the way the language is. And then we have the status quo, and you need to make a proposal to change that. And then we take these polls to decide, do we have enough consensus that we want to change the status quo? And we can always go take polls and polls and more polls. So if, as a paper author, if my paper gets rejected, I have a couple of options. I can come back with another paper and try again. And that's usually like 90% of the time, that's the correct option. Because a lot of times when the committee rejects something, they're saying, we're rejecting it because of reasons X, Y, and Z. And as long as you're addressing those, whether you're fixing the issue or at least saying, I looked into that issue and here's what I determined and here's why I'm not fixing it. A lot of times that builds better consensus the second time around, because people are like, oh, okay, I didn't know. Cool, now I know. The frustrating part about that is as I mentioned earlier, working things through the standard it's a long, arduous process. To give an example, C++ had attribute syntax since C++ 11. And it's in a standard. We've got a bunch of attributes. There's a billion different attributes and compilers. And so we've got a lot of field experience with it. And I thought, this is going to be a slam dunk to bring into C, right? Like, these things show up in header files all over the place. So like C users are going to want to make sure the syntax is exactly the same as C++. This is going to be a total slam dunk. 3 years of meetings to get attributes into C. And at every single meeting, there was contentious topics to discuss. And so you have to have kind of a thick skin and just be like, wow, these people are not getting what I'm saying. Like I must be saying it wrong. I'll try again. and so it can be kind of frustrating. I understand the demotivation aspects because it hits all of us at some point in time. And so, yeah, standards committee work, having a good sense of perseverance and a thick skin can go a long ways.
Yeah, I think that the problem is with C++, and maybe other languages, like, okay, when you have a direction, right, or the idea of something, and everyone knows at the beginning what the language should do, what's the goal of the language. When someone trying to bring something into the language, and it's this person can see clear that this thing that is bringing inside uh, to the language will break or is not going into the direction that the language is going. So these people can be convinced that yes, so it's breaking the values or the idea of the language. But C++ doesn't have it. So that's the problem, and and it's hard to compete with someone that because sometimes because it's hard to convince someone that you're not going to the direction that we want, and if you ask which direction we are going, and no one can answer that question, and it's kind of frustrating because you're saying like when you actually convince that your work is not going is not compatible with the goal of the language, that's okay, you understand it, and yourself, you're a human, you understand, you reason, that's okay, I need to change that. But when you can't see that, right, just see that your idea is perfect, I mean that's the solution, and that's how it should be. I don't understand why they are rejecting my idea. So that's when the frustration comes, because there is no the big picture of C++, what we want for C++. There is no such thing. So that's
it is. I think the thing that surprised me the most when going on the standards committee, truthfully, was just seeing how things get into the language and how the language changes. It was before I joined, I had a mindset of it's going to be the process is going to be this way, and it's going to be a very sensible process. And then when you get into it, you're like, oh, it's actually a little more wishy-washy than that, because there's people involved, and people are kind of, not always consistent. And so, yeah, it is tough because there's not necessarily an overarching, this is the way we're going, and your feature doesn't necessarily fit into it. It's not always clear cut. And sometimes it's we could solve this or we could solve that kind of problems. And it's a trick to figure out which one you need to solve or which one is the appropriate one to spend committee time on, because at least with C++, there's 300 other people involved. And so they tend to be a little sensitive to making sure that we're not wasting anyone's time with ideas. But sometimes I think we can be a little overly sensitive and kill things off a little too early. But
I got an experience with when I was reviewing a paper. Actually, this paper we're talking the range-based for loop. When I was, I would say, amazed with the way Nicholas Jutsus was putting his experience on trying to look in every corner of the language. And I was like, when I was reading the paper, I was like, wow, this is something that you actually can. Of course, you are someone that want to implement something in the language, you need to consider every corner of the language. But he was adding some corners in the language that I don't think I will be able to think about where it come from. It's come with a lot of experience, right? If someone with a lot of experience, like Nicolas Jutsus, for example, can end up in a situation like that, for example, I think it's maybe also affect other young people, for example, that doesn't have a lot of experience. And you say, "Whoa, if you want this giant in the language is being rejected, what about me?" But I don't think this is the direction, and I don't think this is how people should think. I think that you bring up a good example when a high school actually shipped a feature into the language is also a good example, because at the end of the day, we are humans, we all can reason, we all can come ideas, brilliant ideas, and I think that's okay. But it's really amazing. I want to illustrate how C++ is really big. For example, we take in account, for example, parallel programming, how a change in the language can introduce traces, and it's too hard. It's too many corners. I mean, it's a really, 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 really tough job, especially from C++.
Oh yeah. Oh, definitely. And so here's a good example. Here's an experience that I had with regards to rejection. I came to the C++ committee with a thing about has CPP attribute, and we want the same functionality in C. And we got to thinking about it in the C committee, and we're like, well, wait a minute, you can only ever be in C mode or C++ mode. You can't be in both at the same time. So we don't need has CPP attribute and has C attribute. It's one or the other. So why not just name it has standard attribute and be done with it? And WG21, I just happened to get them on a Monday morning when everyone was, feeling kind of tired, and it just got outright rejected for some really silly reasons, and now everybody has to live with it. And we don't always get the answer right because, as you pointed out, we're all humans, and so sometimes we make mistakes. But the thing that I like about the committee is mistakes are generally correctable, and everybody on both committees is really, really dedicated towards making sure that the language is the best it can be. Like that's the one thing that really ties all of us together is we might have different ideas on how to get there, but we all got the same general idea of what we like in terms of we want to make sure it's solid for users and it's fast and it doesn't have a lot of room there for extra performance, leaving it on the table. And so, that it helps to keep those sort of things in mind when you get in those contentious situations where you're like, why are you not seeing how perfect my idea is? It's like, okay, well, at least it's not malicious. They're not doing it because they're trying to annoy me, or they're not doing it because they hate users. It's just they have a very different idea of what the right solution is, and we just have to talk a whole lot more to get to agreement on what that solution might be. And that's the part that can really be frustrating and demotivating, is you can feel like you're talking in circles an awful lot. But I find it helps to at least remember, like, they're only talking to me because they care. Like, that's a good situation to be in. Like, they're passionate. That's good.
Yeah, Alexandre actually put some text here. He says it's a difficult situation. A proposal may seem really amazing to us, but the committee may have other priorities and other factors that need to be considered. Well, this idea that Aaron just mentioned here of having groups that a proposal can go through is really amazing, and I think it's really helpful, because now you have an expert in every corner of the language trying to analyze how this particular feature will interact with the part of the language where they are experts. And I think it's a great idea, and I think it's avoid this kind of mistakes. But the idea here is, like, we are humans. When we bring to the table and it's clear to us as humans that this is a mistake and there is a way to do better, there is no, I think, there's no reason to be upset, right? You just take it and go work again. There is no more conversation. You understand? The problem when you don't see the reason why you are being rejected. So that's when the frustration comes.
Yeah.
So that's what that's what we're talking about here now. When you don't see why you are being rejected, you say, and even you have the majority of the language with you, right? The community is with you. Major part of the community is with you. Oh no, it was really great. And you see that even other people are saying, "Oh, I really like your proposals," and everyone is giving you nice feedback, but you're still being rejected, and you'd understand that you can get frustrated. So that's what we're talking here.
Oh, definitely. And Alexander's point's also really good, though, because the committee, it can sometimes be hard to see committee priorities because we don't really have. It's not like a leaderboard of priorities that we can all go look at. It's kind of different depending on each room that you're in as to what the priorities are, and so it is an interesting process to go through. And Felipe, to your point, study groups have helped a lot with that sort of thing, because now people are getting more comfortable trusting the experts in those rooms and going, I'm not an expert in Unicode, but these people are, and if they say this is the right solution, great, I can just live with that. And I think that helps an awful lot. But there'll always be times when we make mistakes and get it right and get it wrong.
Yeah. So I think we are already out of time. 2 hours 18 minutes. It's really, really, really great for me to talk to you, Aaron. Your session. I've been networking with Aaron at Twitter. I don't know how long already, but it's been nice, and I have been very nice to me to interact with you at Twitter and have you today. Is really, really a great honor to me, and I think it's the same for most of the people that was with us today. So thank you again. Have a good night and see you in the future.
Sounds good. Have a good one, everyone. Thank you all for coming.
Yeah.
All right. Bye-bye.
Yeah. Bye-bye.